and tuning a PID controller. So we just learned how to do, we just learned how PID control works. We just learned how the Ziegler-Nichols algorithm for tuning a PID controller works. And now we're going to apply that to a feedback control system, which is in unity feedback, meaning the feedback transfer function, which we have previously called H, has value 1, so it just feeds back exactly the output of the plant to the summing junction to be compared with the command. We have our controller and we have our plant. The plant has this fourth order transfer function. Okay, so this fourth order transfer function is going to represent the dynamics of the system we're trying to control the output of, and we're going to design a PID controller for it, and we're going to just tune it using Ziegler-Nichols. So that's the design problem. We proceed with MATLAB symbolically at first. So let's define the transfer function symbolically. We have 4 symbolic variables that we'll define, one for the Laplace S variable, and then the 3 gains, Kp, Ki, and Kd. We're going to keep these around for a little bit. And this is, there are several ways to do design in MATLAB with controllers. This is just one way, and I think it's a useful way to do it. So let's start out symbolically. You need the symbolic toolbox, of course. So we'll symbolically define the plant transfer function here, and we'll also symbolically define the PID controller transfer function, which has a proportional, an integral, and a derivative term. So from the preceding lecture where we derived the closed loop transfer function of a feedback system that looked like this, where we set h equal to 1, we found that the closed loop transfer function y over r, both of s, is equal to cg, both of s, over 1 plus cg, both of s as well. So that closed loop transfer function is actually what we're going to solve for. We would like to know how the system will respond in closed loop. When we put in a command, how does the output of the system respond to that command? So we just use a symbolic representation where we plug those into our closed loop transfer function equation that we derived previously, and this is what comes out. We use simplify to simplify the symbolic expression. It's not super simple. Notice that it ends up being 5th order once we close the loop here. It depends. Notice the closed loop transfer function is highly dependent on each of these gains. So Kd, Kp, Ki, they all show up in there. They're going to affect the zeros of the system and the poles of the system in closed loop. So the dynamics of the system are highly dependent on those gains, which is great because those are the things we can control. So now we have a system that has a plant, which we presumably can't control the position of these poles, for instance. It doesn't have any zeros in it. But once we put in the PID controller, we have control of all of these different terms in the closed loop transfer function. So we can affect how the output responds to different commands. So I've created a function sim2tf that creates a TF object, a MATLAB transfer function TF object, which we'll need for simulation. So I just print it out here. This is what it looks like. This is available if you go to this footnote at the bottom of the example. Has a link to the GitHub repository where I have put different MATLAB functions that I've created for doing things like this. So this will allow us to put in the symbolic transfer function, and tell it which symbolic variable we're using as our Laplace transform variable. In our case, capital S is what we're using. And it'll return a TF object. One thing to note, we are going to need, we have to give it a symbolic transfer function that only has, we can't have any undetermined Laplace variables, symbolic variables in there, because a TF object in MATLAB cannot include any symbolic variables. So we have to get rid of those before we use this. So let's wrap it in a function of our own, which we'll call Ksub, okay? Which will create a closed loop TF object from our closed loop symbolic object with the PID gains included. So what we're going to do here is substitute in to our closed loop transfer function, our symbolic closed loop transfer function, the three gains, Kp, Ki, and Kd, which will be the arguments of this function. So if we give, a proportional, an integral, and a derivative gain to this function, it will substitute those into the closed loop symbolic function, and then it will use the sim2tf to convert that to a TF object for us. So for example, I said, okay, if Kp is 1, Ki is 0, and Kd is 0, what is the transfer function object that comes out? And I just printed it out here. So that's nice because now we can simply call Ksub, and we can take our we can take the gains that are used, plug them in, create a transfer function object, and we can do things like simulate what the response would look like with this TF object. So now let's use impulse to simulate the response, starting with a small proportional gain. So we start out and we just say, okay, let's find the impulse response, which is valid. So we could use the impulse response, we could use the step response, or the initial condition response to see when these oscillations become steady. So we use the impulse function, we give it a proportional gain of 1. It's possible we'll need to put in a proportional gain less than 1. It's not, starting at 1 is not a magic number, but we'll try it and we'll see what happens. And it turns out, we plot the result. It turns out that when we set Kp to 1, we get this blue response, which you see the impulse creates a little bump and a little wiggle, but it comes back to 0. If you increase the gain then, so I increased it to 3, the proportional gain, and I did the same thing, and it got a little bit more response. It did come back to 0 though, so then I kept increasing it, and this is a sort of iterative technique to find out when the oscillation becomes steady, and it was right around Kp equals 5.25. So there is a crossover there. When I increased it beyond that, I started to get simulations where the amplitude would grow and it became unstable. So let's take as our ultimate gain then 5.25. And the oscillation period appears to be around 0.56 seconds, which I measured from looking at the peak to peak distance here. It's about a half a second, and I just used the cursors in MATLAB to estimate it was about 0.56 seconds. Defining these quantities, we can now compute what our Ki and Kd should be, and our Kp from equation 1.6. So here was the ultimate gain, here was the oscillation period, and these are the three equations from our step 4 of the Ziegler-Nichols algorithm. And then I just print these out. And our Kp that we choose is 3.15. Our Ki is 11.25, and Kd is 0.22. So let's try out this controller for a step response and see how it looks. So if we do a step response of Ksub and then put in those 3 values that we solved for using our algorithm, and I'm plotting the response in the usual way, we see that we get a response. So this is 2 seconds. We get a response that doesn't appear to have steady state error, although we didn't look in detail here. It does appear to go to 1. When we command it to go to 1, the response, the output goes to 1. And it does that, in about 1.5 seconds. It's settled down to be pretty close to being 1. But it does take, 1 second or so. That might be just fine for the controller requirements that we have, the control system requirements that we have. And it also overshoots, right? So it overshoots. This is called overshoot here. This is a transient response performance concern. Sometimes that's fine. It looks like it overshoots by about 30%, 40%. And that might be just fine for a situation, or it might not be. And so that's the thing with the Ziegler-Nichols method and any of the hand tuning methods. We get kind of whatever they result in, and they're just there for kind of general performance. Now we could now start to tune the gains a little bit by hand. We could say, okay, we have a point where things are pretty good. Maybe if we change this gain a little, that gain a little, we could get better performance. With some criteria, like maybe we want to reduce this overshoot. We could play around with changing these gains a little, turn those knobs a little, and see what the response looks like. And we could adjust our controller design from there. Notice at the bottom here, there's a link to the GitHub repository where that transfer function, symbolic to TF object function lives. So yeah, that's all for the example.